so excellent question. So this is like the residual graph, and to answer another question, so the brown numbers are the residual graph. So the brown numbers are what is left over, and the reason that we are constructing this residual graph is because we edges that have been all used up, we no longer want to think about them when we are looking for paths from A to B. So it's just it's a bookkeeping way to keep track of like how much empty capacity or how many empty seats or how many empty spots in the truck do I have left everywhere in my graph. Does that make any sense, or?
Yes.
Okay. But it's just a convenience. So we don't care about the residual graph. We just want to find the max flow on the real graph. But Ford and Fulkerson had this thought process that actually, if your program is keeping track of these brown residual weights as you go through the program, that will make it easier to find the max flow. So the brown numbers here are the residual weights or the residual numbers or the residual capacity. So and I hopefully Aram, okay. Yeah, so Jan was like, okay, when we found our path, how do we know how much red flow we can send along a path? So if you remember, we had 4 here, 2 here, and 1 here for capacity. And the question is like, how much stuff can we push along this path? And the answer is just take the min of all of the numbers along a path. And the minimum of the numbers along a path is going to be how much red flow you can send along that path. That makes sense, Jan? So the problem that we run into here is that essentially we made a bad choice early on. And again, we had no way of knowing that this was a bad choice. And so it's important that our algorithm be able to recover from bad choices, because we don't have a simple way of figuring out what are the good choices or the bad choices. But when we were just starting off, we sent 2 red units of flow from A downward. And then we had to decide, do we want to send those units of flow up, or do we want to continue along the bottom? And unfortunately, we chose to go up, which for this particular graph is turning out not to be a great idea, because getting stuff from A to this middle node, we actually have like extra capacity we have extra capacity along here and along here. So we could get stuff from A to the middle without using up our the flow from down south. And the flow from down south, actually, like, this edge was more limited than the upward. The northern edge had more capacity than the southern edge. And so, like, it turns out for this particular graph that it would be better to go and send flow along the bottom path, that we could get more flow from A to B if we sent it along the bottom path. So the final key idea here, is to create backwards edges in the residual graph. And so when I say create a backwards edge in the residual graph, what I mean is let's go and whenever we send flow from A down south, let's go and draw a residual edge. And say, because I'm sending to flow from A down south, I could, what this edge is representing is that I could later decide that I want to backtrack and undo that decision. And so this is going to that this is a residual, an option that is open to me once I have sent flow south is I could choose to undo that decision. And similarly here, let's go and draw this. And then let's go and draw, let's say this. This is 1, 1, 1, and then this is finally what I've done is I have drawn backwards edges in the residual graph that represent backtracking. And now let me grab let's use green. So my residual graph has gotten complicated here. And it is unfortunate that my residual graph has gotten complicated, but it is, let's see. So, but fortunately, like computers are good at keeping track of this stuff. So I now want to go and find a way in the residual graph to send flow from A to B using the brown numbers. So here is a way that I can send flow from A to B using the brown numbers. Is I can go and I can, there's a path up to here using the brown numbers. Here, this blue number is still like extra capacity that I haven't used. Then once I'm here, I can't go straight to B because there's a 0 there. So instead what I do is I'm going to send my flow here, then I'm going to backtrack and basically undo the decision to send flow from south to center. I'm going to undo this decision and then go here and go here. So I have now found another path to get from A to B in the residual graph, but in so doing, what I've done is I'm going to be undoing my decision to send flow from south to center, and instead I'm getting flow from A to the center point using residual capacity here. And once I have that flow at the center point, I then no longer need to ship up from the south. So I can undo that decision. Once I undo that decision, I then have extra flow sitting at this south node that came in this way. And so I can go and send that along this green path. So this green path in the residual graph, once I introduce the backwards edges, this allows me to find ways to get more flow to B by rethinking earlier decisions.
So this changes the other path that you made?
Yes, this is changing the other path that I made. And I'll go and like redraw the red flow in just a minute after I erase the green. But yeah, this is going to change a previous path that I'm going to do some essentially some surgery on previous paths by sending stuff up and over, and then once I send stuff up and over, then I can go and pull this flow backwards down south because I need it down south in order to make good use of my excess capacity down here.
Okay, thank you.
Let's see. Are there any other questions about like?
I have a question. I'm trying to figure out. So,
Yep.
Is there any like real world examples of we have already gotten all the flow we need to the target location? Think of the show. Oh, we now have to like do this residual graph backtracking thing.
Yeah. So this is like, I mean, let's say that so let's see. So I think the important thing conceptually is that this backtracking is all on paper. So what I would do is all of the red flow that I'm sending in this algorithm, until the algorithm is done, this is all just tentative on pencil. It's a plan. So I'm planning to send flow up along the top, and I'm planning to send flow from along this zigzaggy path. So I was doing some planning, and before I go and actually like move boxes or move people or like start actually like hitting the go button here, I'm like, wait a minute, could I go and actually get more stuff from A to B? Because essentially I get paid the more stuff I get from A to B. And so I construct this residual graph, and I realize that if I go and erase some things that I had penciled in previously, that I can do better. And once I'm no longer able to find ways using the residual graph to do better, then I say, okay, I am shipping as much flow as I can. Now let's turn the plan into reality.
I see.
So this is all of the stuff that's being done in the middle of the algorithm is just penciling stuff in.
So could it be thought of as like it's really one path and you're just adding layers to it? And so like you're like changing the other layers, but like at the end of the day, like it's one path that you're using?
Well, so, but I might, so I think adding layers is I think it's a useful thought process to think about adding layers. Like, I think that's a helpful thing, but at the end of the day, I am going to want to ship along multiple different paths. So I'm not at the end of the day just finding one path. At the end of the day, my red flow should be a bunch of paths that make the best possible use of the capacity that I have.
Okay, thank you.
Yeah. So again, you can think of it if I'm shipping like I have a bunch of passengers. Maybe there's a weather event that caused some flights to get canceled, and so a flight gets canceled. I've got a ton of people in Los Angeles. Some of them I'm going to have to say like, sorry, you're stuck in Los Angeles, but I want to get as many of them to Chicago as possible using the empty seats that I have available. And so I go and I do this planning process, this multi-step planning process. And then once I'm convinced that I have, I figured out like, okay, how many passengers, what's the greatest number of passengers that I can give good news to? What's the are there 5 passengers, 6 passengers that I don't have to say tough? I can actually find them a way to get to Chicago despite the cancellation. Then like I send out all of the email notifications or text messages simultaneously once I've figured out, okay, there are 3 paths that I can use through the country using my empty seats. And if I use all 3 of these paths, I can get like 7 passengers from LA to Chicago, and the rest I'll just have to put up overnight and deal with them tomorrow. Let's see. So, yeah. So let me answer Jan's question next, which is, okay, I've found this green path. And Hunt, I see your question. I will answer it in just a minute. But so Jan asks, okay, we found this green path. Now, what do we do with this green path? So I'm now going to erase this green path. But hopefully you've been staring at it long enough that you can see that it's that path. So I'm now going to go, and I guess the first question on this green path is how much flow can I move along this green path? This green path allows me to get how much extra flow to be. And the answer is 2, because 2 is the smallest residual number on this path. This is 2, 2, 2, 2. This one was a 3. But what we're interested in is the bottleneck, the minimum number. So the smallest number on this path is 2, so I can move 2 units of flow along this path. And so what I'm going to do then is I'm going to go and add from this 1 is going to become a 3. Then I'm now going to be sending 2 units here. And maybe this is I think I was writing these next to each other. So this is a 2. And then this will be a 2. And this will be a 2. And at this point, what I'm doing is, because I am backtracking here, I'm using the backtracking edge, then here what I'm going to be doing is actually going and deleting flow. So I've added 2, subtracted 2 because I was using a backtrack here, added 2, and then I go and I update my Brown capacities. And so this 3 now becomes a 1. There's 1 capacity left here. I could backtrack 3 if I wanted. This becomes a 0. There's now, I'm using 2 capacity, so there is none left here. Oh, and I would want to draw in a backtracking edge. This backtracking edge goes away because I'm not sending flow, so I can no longer backtrack here. Then let's see. Then here, these also are going to become like 0s. There's no capacity left here. There's no capacity left here. And we will go and draw in our backtrack edges. So at this point, there's a question of, can I find a path from A to B? And at this point, the answer is that there are no paths that are using this Brown residual capacity to get from A to B. And one way that I can convince you of this, so like you could just run depth first search and you will find that because there's like no capacity here, no capacity here, no capacity here, you're not going to find a Brown path that has leftover capacity from A to B. Also, it's the case here that, like, it turns out that all of the edges into B are now fully loaded up, which is, like, awesome. So, oh, I'm sorry. I realized that I now need to, we've still got 2 capacity here. So, like, we've got some capacity. I can still, like, go up here. There's a 1 capacity up here. I can go up here. There's 1 capacity, but I can't get any farther there. There's no capacity left to get into the middle. There's no capacity to go down here. So at this point, in my residual capacity graph, there is no way to get from A to B. And in fact, you can see that all of the edges into B are being fully used. Now, that depends on the graph. So sometimes the bottleneck will be, like, coming into B. Sometimes the bottleneck will be going out of A. Sometimes the bottleneck will be somewhere else entirely. Does this answer your question, Jan? Yes. Okay. Excellent. So then I realize that this is a little messy and it involves a lot of bookkeeping, but, like, computers are good at this kind of bookkeeping, keeping track of, like, how much residual capacity is there left over on each edge? Do I have a backtracking edge? If I have a backtracking edge, how much capacity is on the backtracking edge? Like, these are all things that computers are good at keeping track of. So at this point, I want to jump back to Hunt's question from a little while ago. So let me see if I can go and undo us back to a point where we can talk about this, like, backtracking. Okay. Okay. So Hunt is, so this was the point, I believe, where we went and found a path, so where the brown numbers were greater than 0. You had capacity here, use the backtrack edge, go this way, right? That was our green path. So Hunt, what was it that you wanted us to play around with? You said you wanted to change a number. Which number? From the center. Okay. So is it the center and B? So I think it was, like, right here. So this is, I think. So I think Hunt was saying, what if we had an extra piece of, what if we had an extra piece of capacity here? So, so if we had an extra piece of capacity here and we're looking for a path from A to B, then there's 2 different options. I can either use this path that we used before, or I could use this path, which now this path, the second green path, actually has capacity, because in Hunt's hypothetical world, there was a little bit more space available on this leg of the trip. So we still, when we're looking for a path from A to B, we can pick either path that we want. Again, if you're using like breadth first search or depth first search, like it might depend a little bit on what order you're going and exploring the graph. But just hypothetically, let's just run this out using, okay, let's say I pick this path. So here, if I pick this path, then I'm going to go and ship on an extra unit of flow here. I'm going to ship 1 unit of flow here. I'm going to turn this 2 into a 3. No, that's probably ugly. So I turn this 2 into a 3. And then that's, yeah, boom. I've just gotten some redness here, boom. And then I now update my residual capacity. This is a 0. This is a 3. Because I now have... and now this 2 is going to become a residual 1. And I can add a backtracking edge. And here, this 3 is now going to be a residual 2. And I've got some additional backtracking I could do here. Okay. So in this case, we picked a path and we sent 1 unit of flow along this path because that's all the path could accommodate. We're now down to 0 here, so we couldn't have sent more than 1 unit of flow along this path. And then we updated the residual graph. And so now the question still remains, is there a way to get from A to B in the residual graph? And so we put off the need to backtrack, but we still do need to backtrack because there's a path here, 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 backtrack, here, here. So this path now, in the previous example, before I went and like added some additional capacity here, this backtracking path was a path where I could get 2 more units of flow to go along the path. Here, however, in our new reality, I can only send 1 unit of flow because this is the bottleneck. Because I'm already sending 1 here, I can't go and send 2. So what I would end up doing is I would end up going and backtracking 1 of these 2 units. So instead of backtracking all of the 2 units, I would backtrack 1 of the 2 units. And I would only end up using then 1 of these 2 capacities and 1 of those 2 capacities.
But doesn't the third edge in that green path that you had highlighted before, doesn't it have a capacity of 0? So doesn't that mean you can't
so this, okay, let's look at this. So this is the, like, the green path here was here, here, then back. So this has 0 capacity in this direction. I'm already full going from south to center, but I can go and backtrack up to 2. And then here, and then here.
Okay.
Does that make sense? So no. So there's a separate. Is this the edge we're talking about? This one right here?
Yeah.
Yeah. So this has a separate capacity in both directions. So I'm currently, my tentative plan is to ship 2 things north along this edge, but but that turns out to be a mistake. And so I found that if I go and backtrack one of those 2 units using this backtracking edge, the backtracking edge still has capacity. And the capacity of a backtracking edge is exactly the amount of tentative flow that you're sending in the forward direction.
If that's true, if the backtracking capacity is always the amount that you're tentatively planning on sending in the forward, wouldn't you always have either backtracking capacity or forward capacity?
Yes, you will always have, yes, on every edge. Thank you, Courtney. That's actually really helpful. So in our residual, in our residual graph here, for every edge, so this edge we have 2 more forward capacity and 2 backtracking capacity. This edge, 1 forward capacity, which is this brown number here, and 1 backtracking capacity, which is this brown number here. Here we have no more forward capacity because we're using it all, but we do have 1 backtracking capacity. So yeah, so you will always have the sum of the backtracking capacity and the forward capacity, like in your residual graph, in these brown numbers, the sum of the forward and the backwards will be your original blue number, your original blue capacity to start with. And what that means is then, yes, on any edge, either it's the case that I can ship more forward, or it's the case that I can backtrack, or in some cases, like here, I might have an option either of shipping more forward or of backtracking. Both of those options are available to me.
So I'm sorry, what tells us when we're done or not?
Okay. Yeah. So I think Eric just caught this, is that, yeah, so we're not done here. And the way that you know whether or not you're done is, can you go and find a path from A to B in the residual graph? So using these brown numbers, can I find a path from A to B that doesn't involve any zeros?
Which brown numbers? The ones on the arrows or the ones on the edges?
So this is either. So the everything here is arrows. So like here, this 2 is 2 on the arrow going up, and then I also have 2 on the arrow going back, which is my backtracking edge. So I'm looking for a path from A to B, and I'm allowed to use either forward arrows or backward arrows. But I can't, for example, I can't go here, here, and here, because if I'm trying to go from the top down to B, there's a 0. So there's a 0, there's no way to pump more along this green path. So what I'm looking for is a path from A to B that only follows arrows that have brown capacity left over. And again, everything is an arrow. Some things are like, the original edges are all had an arrow on them, so they're like forward. And then I drew in these imaginary backward arrows in order to represent backtracking.
Okay, thank you.
So let me just finish this off. And a way that I can finish this off is by, here's a path, and I run this path, and I can send 1 unit of flow along this path because this right here is the bottleneck along this path. This is the minimum brown number along this path. So this path doesn't have any zeros, which means this is a good, valid way to get more stuff to B. It involves a little bit of backtracking, but that's fine. So I'm going to go and push one more unit of flow. I'm going to push one more unit of flow along here. I'm going to push one more unit of flow along this edge. Then I'm going to use the backtracking. And when I use the backtracking, I am now going and conceptually erasing flow. Conceptually, what's happening here when I backtrack is I want to use these edges, these bottom edges. And so in order to use these bottom edges, I need to get more flow into this node right here. And I can't send more stuff directly because I can't send more flow directly because this is already at capacity. So one way that I can get more flow at this southern node is to cancel my order, cancel my intention of sending up along this path to the center. And by canceling that, I end up with leftover flow here. My flow in is now greater than my flow out. So this is like a, I guess, this is my flow in is now greater than my flow out, and so then I can go and send it here and send it here, and so then this is like a 1 and a 1, and then these numbers are get residual capacity. There's and then let's see, that was a 2 here. This is now a 0, and this is now a 1. This is a 3. Just going and updating all of the brown numbers in my graph. And then this is oh, and then there's like backtracking edges here and here. So I believe this is correct. And so now this is, at this point, I'm claiming that we're done because I'm claiming that there are no longer any paths from A to B that only follow arrows with positive, not like, I think all of the paths from A to B involve going through a 0. And the way that I would know that for sure is I would go and do like breadth first search or depth first search or something like that to do a pathfinding algorithm. Yeah. So I think this is the end of my explanation of Ford-Fulkerson. So I'm going to, in just a moment, I will do a summary slide of Ford-Fulkerson. But before I go and put away this graph, is there anyone who has any questions about this? Okay, so oh, I need to change the oh, I see what it is. Aha, no, I only backtracked 1. Thank you. I didn't backtrack all the way. I only went and backtracked 1. Thank you. So yeah, in this example, I was sending 1 flow along the backtracking path. And so that, yeah, that's, yeah, so that was a, yeah. So I was only undoing one unit of flow, so I didn't want to erase the red altogether. Yeah, so okay. Yeah, thank you, Maria. That Hacker Earth article is useful. I will grab that and make sure that I send out that link on a Canvas announcement at some point as well. Yeah, so this is what Hunt said was wondering was what if you're trying to loop? And so I think I'm not going to spend time right at this moment going into a loop situation. So when you're looking for paths from A to B, if you are looking for a path from A to B, then your pathfinding algorithm should avoid loops. And one of the ways that you can like avoid loops on your pathfinding algorithm is to just keep track of the nodes that you visited already. Keep track of the nodes that you visited and don't consider finding a path that has a loop in it. So if your pathfinding algorithm that you use as a subroutine, if that never does any looping, then overall this algorithm will not, you're never going to create a loop in the process of running this algorithm through multiple iterations. You probably shouldn't take my word for that. Like it's an interesting thing to think through. I don't have a clean proof right off the top of my head, but it might be interesting to play around with an example. Maybe this is a question for a final exam. Probably not, actually. I don't think this is a good final exam question. But if you look at some examples and think about how a loop might come about, then you should be able to convince yourself that the only way that a loop would actually happen is if your the only way a loop should actually happen is if your pathfinding algorithm returns you a loop at some point. And every iteration of this is going to go and continually get, every time you iterate and go and make some adjustments, you are ending up with more flow going from A to B. And when it terminates, you will have found the maximum flow. Let's see, are there any other questions here in the chat? Okay. Yeah, so this is, I see what the problem is. Okay, so I'm sorry, I misunderstood your question, Hunt. What Hunt was wondering is if you backtrack and then you unbacktrack and then you backtrack and then you unbacktrack, are you actually making progress? And the answer is because every iteration of the algorithm ends up with more flow going from A to B. You start with like 2 flow going from A to B, and then after you go and do an adjusting cycle or an augmenting path once, then you end up with strictly more flow from A to B. So you go like 2 and 3 and 4, and then maybe you jump from 4 to 6, but you're always getting you're only making adjustments if it will get strictly more flow from A to B. And because of that, you'll never end up back in the same exact state of the algorithm. The algorithm must terminate because there's only so much flow that can be sent on the graph. And every iteration, you are going and making a strict improvement. So this is a general like argument technique in algorithms when you say like, could my algorithm run forever? Could I get stuck in an infinite loop? Or must I eventually stop? And here, because every time through the main loop, every time that you are going and finding an augmenting path, you are strictly increasing the amount of flow you send from A to B, then it can't be the case that you loop forever. Okay. Thank you. Excellent. So then I'm going to go quickly here and pull up. I tried this for another class, and it worked reasonably well. So I just wanted to provide here an overview of Ford-Fulkerson. So overview of Ford-Fulkerson. So this is so start with a directed graph, find a path. So this is now, then you figure out the max flow for that particular path, which is the min capacity on the path. And then what you want to do is update your current flow numbers to send this amount of flow along the path. Then repeat loop. The like residual capacity, the flow in and okay, so this is a high level look at Ford-Fulkerson.